been scared that there are this many of y'all. So
We will be nearly as intimidating as your thesis advisors.
And just as a reminder, the idea is to interrupt Chelsea a lot and ask a lot of questions, and she's prepared for there to be lots of opportunity for questions. So
Yeah.
don't let me be the only one.
So we're gonna start off in R2. So the normal coordinate plane. And we're gonna start out with matrices we all know and love. Think of 1, 0, 0, -1. Remember from our math 3-4 book, this is a reflection. Does anyone remember what it reflects over what line?
X-axis.
The x-axis? Is that right?
1, 0 goes to 1, 0, 0, 1 goes to 0,
Okay.
Okay, and so all reflections in the real world are actually of order 2, meaning if you square them, then you get the identity. So all real reflections, when squared, equal the identity. And so this is one of the areas of research that has been very, very well studied. A lot is known. They've done a lot on real reflections. And you might wonder, okay, so if all real reflections are order 2, are there any other kinds of reflections? And you might think, well, what about complex numbers, right? And so there are more than just order 2 reflections in the complexes. You could have, say, 1, 0, 0, omega. And here, think of omega as something like, so in our terminology, we would use like cis of 30 or something, right? Where when you multiply this by itself multiple times, eventually you'll get back to cis 360, but it takes more than just 2 times to get there, right?
Sounds like a rotation.
Yes, but it's a, okay, cis 30 might not be a reflection. That one was off the top of my head. Please forgive me, I didn't study complex reflection groups very much. So ignore this example. It needs to be, wait, isn't cis 30 a root of unity though?
So,
Yeah.
so you're solving m squared equal I. You're looking at all matrices 2 by 2 that pretty much, solve that.
Right, but
Right.
there has to be an additional premise.
Yeah.
Yeah, so the
That's
additional premise that I'm gonna say is that,
So, yeah, you need to bring that constant is important.
so
So the determinant should be probably
we generalize reflections
plus by minus 1.
in F, and here F, just think of F could be R, it could be C, or it could be what we're gonna talk about, which is FP, which I'll explain later, ignore for now if you don't know what that is. That's a C, that's not an E.
Yeah, Chelsea.
Complex.
Yeah.
So we generalize reflections in Fn, this is a vector space, to be a transformation, which we'll represent as matrices, that fixes a hyperplane. Okay, so what's a hyperplane? Well, in R2, it's just a line. It's something that's one smaller dimension than the ambient space. So this is a case of dimension n minus 1. So in R3, well, in R2, it's a line. In R3, what would it be?
Right.
Yeah. So as long as it fixes it, and how does it fix it? Well, it has to fix it. I kind of should have.
Does it have to be a line through the origin, a plane through the origin?
Wise.
Does a fixed hyperplane have to go through the origin?
The origin's
No.
always fixed.
Okay, it's a linear transformation.
Yeah.
Okay.
Yeah.
So it has to
Sounds good.
Yeah, it's near. This.
So, in other words, I can't just take this line, let me use another color. I can't just take points on this line here. This is my quote unquote reflection line. I can't just like take this point and move it over here and consider that a reflection. I have to take this point and it has to get sent right back to itself, as well as like, you know, reflecting things over. So the way we're generalizing is we're saying that it's a reflection if it takes points on this line and sends it back to themselves. Fixed point, yeah. And then this whole line is made up of fixed points. That, for this instance, the line x equals 0, this matrix sends all of those points back to themselves, right?
So can I clarify definitions of it? Can I ask a question?
Yeah.
So is that correct? Okay, that same.
Is that in R3, Aaron?
Are we in the
Secret.
complexes?
Yeah.
C3?
So like,
So what you want to do is you want to think about how it acts on a vector. So if we just take an arbitrary vector with coordinates a, b, c, right? How does this affect that matrix? So sometimes, in some cases, it's easier. So in our classes, we think of the unit square and how it affects the unit square. You can do the same thing in 3 by 3, except instead of the unit square, we just do the unit cube, right? So 1, 0, 0, how does it affect this? Well, it takes it to just 1, 0, 0, right? And then, did I do that right?
Well, don't we need to know what's next?
There are other spaces
Any
are
place
0.
where it's empty is a 0.
Oh,
Okay, so take, yeah.
It'd be nice to know.
Yeah, sorry, I should have mentioned that.
I thought it was just a whole other place for any number.
No. Any empty space is a 0.
Okay,
And so then it takes 0, 1, 0 to 0, omega 0, right? And it takes 0, 0, 1 to 0, 0, omega. And the question is, does it fix a plane? It doesn't have to be on one of the axes. It could just be a plane that is like x plus y plus z equals 1, right? And if it does, then it's a reflection.
So this would fix x plus y minus c equals 1 or something like that, because the omega and omega are equal and 1 were equal,
Yeah, I think this
something like that.
fixes essentially if you create the arbitrary a, b, b, right? This is a 2-dimensional. There's 2 degrees of freedom. I can make any choice for a, and not with b. B. This needs to be. What is it? Should be a way. Again, complex numbers are not my like area of expertise, so y'all need to help me figure this out.
Okay, the thing that the reason I asked this question is because to me, it's like you said, if you're looking for like a plane that gets fixed by this, one choice, you have 2 degrees of freedom, like you said.
Yeah, you should have 2 degrees of freedom, yeah.
Right. So you could either have like the things that look like a whatever, like a 0, 0. But on the other hand,
That doesn't fix those.
those are not fixed.
Yeah, so I don't think that's a reflection.
Okay. because everything, there's sort of 2 degrees of freedom that are fixed.
Yeah.
Kind of, okay.
Yes. Okay, cool, good question. All right, so now I'm not in, like I said, the complexes or the reals. And when you go to graduate school, you really like narrowly focus on one thing. And then when other class questions about other things, you feel like you know nothing, which is very true. So I'm in FP. And what is FP? Well, let's take an example. F3, we can just say is the set 0, 1, 2. And we need a multiplication, addition, and division for it to be just like the real numbers, just like the complex numbers. So addition, I'm going to say if in R we add to 3, make that 0. So 1 plus 2 would be 3.
Congruence.
Yeah, so we're just doing modular arithmetic. I don't know that everyone knows what that is, so I'm trying to. Yeah, so this is in R. So in our world, it becomes 0.
Like taking a remainder after dividing by 3?
Yeah, so just take a remainder after dividing by 3, and that'll give you what it adds to. So if I wanted to do 2 plus 2, this is 4 in R, so it's going to be 1 in F3.
Chelsea, is there only one operation?
No, there's multiplication also. It's just like the reals and the complexes, and that it has every operation you could ever hope for.
I have another question, sorry, going back to this generalization of reflection. Does it have, is there any invertibility criterion or criterion about how to invert it?
It ends up that they will all be invertible matrices. All reflections are invertible.
And does it have to be self-invertible, like a reflection in 2 spaces where it's its own inverse?
No. In the real numbers, it will always be.
Yeah.
But the generalization, no.
Is that because you're gonna end up with more higher orders for these reflections?
Yes. Yeah.
My understanding is that like order 2 and self-invertible sort of mean the same thing.
Yes. Yeah. And we also have multiplication, and it's going to be the same. You just take a remainder. So 2 times 2. What am I trying to write here? Is 4 in the reals. We're going to make it 1 in F3. So let's do another example, which has more things. And we can also, if we wanted to, if we want subtraction, we could say, okay, well, -1, that's the same. We can identify that as 2, right? So we can say minus x if we want to do that, so that we can have the polynomials like we always wanted. So
Can't live without polynomials.
in F5, if we have, let's say, 2 times 4, what would this be in F5?
3.
3, because it's 8.
You wanna write out what
Was
it-
that in the reals and the 3?
Oh, yes,
Just
thank
move
you,
your
thank you.
arrow.
Yeah.
Shift your arrow.
Because there's no harm in also allowing these to F5 as long as you keep in mind that it's the same as 3.
Yeah. So we also have division, and I'm not going to prove this, but you can check on your own that the multiplication here, you'll never multiply any non-zero numbers and get 0 for anything, as long as this is a prime.
Okay, so he is a prime.
So that's what makes this just like the real numbers.
Is it always 0, 1, 2 up to that prime? Is that what this set?
Up to
is?
p minus 1.
Oh, that's right, 3. I'm sorry, I saw the 3. Yeah.
Now, there is an extension I'm kind of fibbing. You can actually have it be a power of a prime, but we're going to ignore that possibility and just focus on being a prime, because those are things that we can actually visualize very easily. And when I was doing my examples in my thesis, I pretty much only worked in primes and then just extended later. So it's better to do examples in this smaller case. Okay, so what do reflections look like we're still going to be 2-dimensional. I feel like that's best for now. So reflections in FP squared. And most of my examples are going to end up being in F3 or F5. So we can have the same sort of reflection where it's a diagonal matrix. And here A could be anything except for 0 or 1.
In that set, or just anything.
So here A is in FP, but A is not 0 and not 1. Because if it were 1, then this is the identity, and that's,
Doesn't matter what you do, but.
yeah. And if it were 0, then it's not a reflection. And you can sort of verify that. So that's one possibility. So for F3, that's really gives us one example is 2, 0, 0, 1, right? Or you can think of it as -1, 0, 0, 1, is the same as our original matrix. And of course I can have it like this, right? Now there are other reflections than this as well, and they're called transvections. And these reflections do not have the type, and they don't have an analog in the reals. So these look like 1, 1.
Sorry, I got
0.
excited because the word for shear, which is what that is in French, is transvection. It's the same word, so.
And it's because, so that's the, so y'all remember the math 3-4 problem. If you take this to the n power, this becomes 1 n 0, 1, right? Well, if you're in FP, eventually that goes back to 0 and goes back to the identity. So this is a reflection in FP and not in the real plane because of that. So it can be proven that you can essentially, with a clever naming scheme, get all of your reflections to have this form, these two forms in FP. And the same thing is true in the reals, by the way. If you wanted to, you can sort of do a clever renaming to get like them to look a certain way and have a basis if you want to, where you only have to name a few of them and it generates the whole batch. So
Can you say more about what you mean by that? Like be a little bit more specific, at least in the reals?
yeah, so the reals have essentially you can reduce it down to like a finite collection of matrices that will then generate all of the reflections. So my best example would be in this world again, would be to just say, I include things like this. I also have to include things like
It's like having a basis.
this. Yeah, it's like having a basis.
So you mean like your reflection is just reflection across the x-axis like we had at the beginning, but then you have a basis transformation so that you get reflection along any other line. It's basically the same.
Yeah, so like in the math 3-4 book, when we had 2 reflections, that creates another reflection.
Rotation.
2 rotations, that creates another rotation. I thought we had one where we had yeah, okay, that too.
2
Reflection
reflections
is
in a
rotation.
Yeah, yeah. Okay. Yes.
It's composition. You have two of
They
them.
only differ by a slope.
Right.
Yeah.
The
So
lines only differ by a slope.
Yeah, just turn your head, it's the same
Yeah,
reflection.
I need to
Yeah.
correct something.
Yeah.
No, you're right. I need to correct something. So we call a reflection group a collection of transformations generated by reflections. So rotations are part of a reflection group, though they are not themselves a reflection because you can create them with 2 reflections. And by generated by, I mean like you multiply 2 matrices together and it gets you a new thing, a new transformation. So yeah, rotations that are generated by reflections would be in this collection, this group.
So can you go back? So you're saying this transvection and the 2 reflections that you listed, those the only, like all reflections can be generated from those 3 things?
The reflection group, yeah, generates from those,
Just those 3?
yeah. Essentially, you just have to choose a clever, yeah.
What do you mean by clever naming? I mean, I can see that you're trying to not go into it, but do you mean like What do you mean by clever naming scheme in this context?
Just a change of basis.
Oh.
So, sorry, again, with it, to confirm that. Sorry. It's a good indicator, like, like in R2. You said, right, did you say in R2 what all reflections are? Like, is it a similar statement you can think about R2?
She only said you can make a similar statement, but she's not gonna go into the details.
So I actually don't know it off the top of my head. It'll take me a lot of work to get it.
I think, okay, I can guess, I can try to guess it off the top of my head. Question mark here. And the reason is, okay, the reason I make this claim is just because reflections look like you pick a line and then you reflect across it. It is, you can always choose a coordinate system so that gaps along. But
Sounds right.
you can always choose a coordinate system so that the thing you're reflecting across is like, okay.
Yeah, when you change the coordinate system, it does change what the other reflections would look like in your matrix form. But it's easy to just think of these basic ones when doing examples because all of them can sort of be renamed to look like that. So now we're going to talk about reflections and polynomials. So we know that you can multiply a matrix times a vector, and that we call an action. But we can also define functions so that we can have an action on functions too. So I'm going to define functions. X is going to take f2 to f. So think r squared to r or fp squared to fp. Where x, we feed it a vector. And all it does is it picks off the top coordinate of that vector. Just picks it off. That's all it does. And we're going to define y, you can probably guess, to pick off the bottom coordinate.
Source projection.
Projection. Yeah. Okay, and so the matrices we would hope would be able to also have an action that acts on these as well, because they're very much tied to the vectors that they're defined by. And in fact, they do. So if you take a matrix M, a function F, even one that's made up like multiplying, squaring, all the different polynomial things you want to do, and vector B, then how you act on this function is, well, you have to first feed it a vector, and the way it acts is going to be the same as if you take M inverse transpose times the vector. So inverse transpose, I'm just going to write as minus t. So if you remember inverses, with 2x2 matrices in the reals, so in R2, inverse is just 1 over AD minus EC times, oh, I can't remember the
E negative B negative C.
Okay.
I'm assuming that they were adding C. You just switch A and D and make it
Yeah.
A and C.
So just like in R2, we have inverses in FP and inverses in C, but it's a little bit more arithmetic and changing your brain thinking to figure out the inverses in these worlds, because you have to change the way you think of them. But yeah, and then the transpose. So if I take A, B, C, D and I transpose it, this is, you keep the diagonal the same and you just swap the off diagonal.
columns become rows.
Yes, all the columns become the rows.
And can we only work with square matrices in this world?
Yes, yeah, we're gonna be working only in square matrices, because we're working in, the two.
Oh, right.
Yeah, and the reflections are transformations of it, so they need to be square to have inverses, right? So what does this mean? Well, it means it's going to, let's say if we have x, and we're gonna act on it by 1, 1, 0, 1, and we're gonna feed it the vector AB. Sorry, that's not, yeah, and x is our x that we want. Well, so I'm gonna do the inverse transpose. Y'all can do these calculations later if y'all want. The inverse transpose at F3, I believe, I might be wrong, but I believe it's this. It's either that or it's minus 100, I can't remember. It's one of those.
Stephanie, can you tell us why it works?
Well, okay, first, if I first do the inverse. Yeah, we just, switching A, B, but.
It could be 1, 2, yeah.
And we're dividing by 1, and then you want to transpose it. Oh, so shouldn't this be there?
So no, so the inverse of this, because remember, when you multiply
Oh,
this by
yeah.
this
Oh,
in
yeah.
F3, this gives you 1, 3, 0, 1, which in F3 is the
That's a
identity.
zero, yes.
Oh,
So that is the inverse?
So this is the inverse of this,
Okay.
and so this is the transpose. So you can put it 2 weird steps. So this is the inverse of that, so this is the
But there's
inverse.
no three.
Yeah, okay.
Go back.
Yeah.
I'm surprised there was a -1, frankly.
Oh, I put it instead of 2, because sometimes.
Yeah.
But, okay.
One is two.
So now what we're gonna do is we're gonna multiply this by the vector AB, and then pick off the first coordinate. And so this becomes x of, so then we'll have a in the top coordinate, and then 2a plus b in the bottom coordinate. So this is just a. Now, there's a whole bunch of theory as to why this is exactly the action you want. Let's put that in a black box and pretend we all agree this is the exact action that we want and need to satisfy the properties we want.
Chelsea, can I ask a question?
Yeah.
Sorry, I came in late.
No worries.
I'm not worse students. Why are we calling the x and y coordinate functions reflections? Or
They're
are we
not.
calling projections?
They're not reflections. As reflections and polynomials, I'm defining the polynomials, and now I've defined how a reflection is going to act on the
Oh, I see.
polynomials.
Okay, fair enough.
Yeah.
So that's the action you're developing through your matrix.
Yes. And so, for example, if so you can show that. Okay, and remember how this 2, I can think of it also as a -1 if I want to. And to make it easier, I'm just going to write it all as a negative instead of a 2. Something's wrong with the paper, or something's wrong over there.
It was Stephanie's calculation.
It was my
Just
fault.
kidding, just kidding.
I was just doing the inverse.
You can put the -1 back if you want.
X of that is X, and then that's.
But just doing the inverse, there's no multiplication going on calculating the inverse. So I don't understand why my inverse wasn't correct.
Oh, it's fine. But by the way, is the commutative inverse and transpose? Is it possible you have to take the transpose first and
No,
do the
no,
inverse?
it doesn't, the
Commutative?
order, it doesn't matter.
Okay, so I think
That's a
you're
good
right.
question.
I think you're right.
Or the determinant.
And the determinant is 1, so it should be 1, 0, -1, 0 is the inverse.
I mean, I think the reason why they're commutative helps me understand why the second.
Okay, 1 plus 0, okay, 2 plus 1, that gives you 3. 0, 1 no, this is right. This is definitely the inverse.
Okay.
And this is definitely the transpose. The reason why I'm
negative 1 is 2.
Yeah.
Yeah. The reason why I'm confused is because for some reason. Oh, yes. Okay, now I know why I was confused. All right. So the question is then, what is this the same as? Like, how could we rewrite this as the function? Well, this is just our original function x acting on v as well. It has the same value. So what we say then is that this matrix times x gives us back x. But if you look here, so x should give us a, and y should give us b if we were doing the original vector, just the original vector. But here, if we take y of this, I need to write it. If we take y of, so if we take this matrix times y, and we feed it the same vector, then we should get minus a plus b, right? Based on the work over there. Okay, so remember though, x of ab was a, and y of ab was b. So in some sense, it's like you're taking, you could instead replace this as minus x plus y in some sense and write it like that as shorthand. Because that's what you would have gotten if you had done minus x plus y instead of the transformation. So, and for some reason that I can't figure out, in my paper I have x minus y and I can't figure out y, and that's how I have it all the way through.
Your published paper or just your piece of paper?
Both, because I went off my published paper. So I'm doing something wrong here, I don't know what it is, but it's off by a constant, so are we okay?
I'm fine with leaving the constants.
Can you explain again on the left what minus a plus b?
Oh, well, that
Yeah,
requires
second
some
one,
y
yeah.
to it instead of function x.
Second component.
Oh, okay.
Yeah, so I don't know what I did wrong, but what we're gonna say, we're gonna pretend somehow I got it to work the way it does work, because I believe my advisor that I had done this work correctly at one point in time.
Sorry, you're saying that the thing you want to be getting is a minus b.
I want to be getting x minus y.
Yes.
A minus b.
So
Yeah.
there's some,
That's what you should have. Maybe, I mean, okay, there's a way I like to think of these, which to me, I think in my head clarifies what's going on. Is it worth going through that with the hope of understanding why you get a minus b, or is it better to just leave that for?
So y'all keep going.
Yeah.
there's some polynomials that are going to kernel of this.
Yeah.
Yes, I agree that it should be a minus b.
And I did something
Although I
wrong.
don't know
Can you
that I
see
don't
what
know
I
that.
did wrong though?
All I can do is do it the way that I is more familiar to me, and see and agree that.
Yeah, I don't know what I did wrong. Okay, well anyway, let's pretend like I did it right somehow, and that this actually will give us x, and that, no, x. Oh, I know what I did wrong. Yeah, okay, so I was doing something weird, and I don't know what it was. Okay, I apparently was working with the ones down here for some reason, or I don't know, something was wrong. Let's pretend that we're in this world. You can just rename it, and there is a renaming that gives us this. That was apparently the naming I used in my paper. So what it's going to do is this matrix is going to take x to x minus y, and it's going to take y to y. And then the matrix 1a is going to take x to x, and 1a is going to take y to ay. To a inverse y.
You just relate your x and y here. what was X is now known as Y,
Yeah,
and what was known as Y is now.
yeah. But I don't know why, like, 'cause I'm pretty sure this should have worked to get the correct labeling, but it didn't, so I don't know. I'll figure it out one day and come back to you. Okay. So let's take a polynomial. Let's take, for example, x cubed minus xy squared, and let's affect it by this matrix using these rules.
Did you figure it out?
I think so. Well, I mean, it's been a long time, so I don't know, but if you see service.
You want to write it on the board?
I started doing the inverse first, so if you do 1, 1, 0, 1, and you do the inverse, don't you get 1, 1, 0, negative 1, 1? And then when you do the transpose, don't you get, doesn't the negative 1 come up here? So shouldn't it be 0, 1, 2, or sorry, 1, 2, 0, 1, shouldn't it? Oh, sorry.
But isn't this the inverse of this? Just when
Yeah, that's what you
multiply
have.
out?
You have the same thing.
But in the end, when down
you move
below,
the
you
two.
move the 2 down to the
Because
bottom
that's
left.
transpose.
But I already transposed it, that's what
Yeah,
I'm
you
saying.
transposed twice.
I took this matrix. I found the inverse of that matrix. And then I transposed it. I didn't transpose it twice.
When I do the inverse, well, I don't know if it's worth spending time on it, because I can be very wrong, so. I just did the inverse first. I
But
got
that's not
this.
the inverse. That's not the
That's not the inverse.
That's
No,
not
the inverse
If
stays
you
on the top.
multiply them, you don't get 1, 0, 0, 1.
Oh, no, it's at the top.
The A and B switch in the inverse, not the C and the D.
These two switch, and so 1 is in 1, and these two get negated. I moved that person.
Oh, that was it.
There we go.
I thought I did the same thing. I think it's because I was sitting.
Yeah. Like inevitably
You were
comes
sitting
off.
next to me. Sorry, it makes time.
No, no worries. I mean, we're supposed to all understand it. Apparently I flubbed something and can't figure it out. So what would this do? Well, it would send x to x minus y. So this becomes x minus y cubed. Just anywhere you see an x, replace it with x minus y. And anywhere you see a y, well, I'm just going to replace it with a y because I'm acting on it by this matrix, not by that matrix. This matrix just sends y to y. Okay, what does this equal? Well, we know this because we all know and love the binomial theorem, right?
X and Y are commutative.
X and y are commutative, yeah. Okay, but we're in F3.
3 is 0.
Yeah.
So we have what's called freshman's dream. Locally known as freshman's dream, that if you take it to the p, so freshman's dream is that x plus y to the p equals x to the p plus y to the p in my land.
Oh, yeah.
So,
It is almost never true that.
whoa, it's the same. That's so exciting. I'm excited because that's what's called an invariant polynomial. So this polynomial is invariant under the action of our matrix. And these have a very special, they're very well studied, they're very of special interest to algebraists and to physicists. But don't ask me what that is because honestly I don't know. I just know that it is special from being told so. I'm sure someone else like Jeff could give you more information, but I cannot. So we care about invariant polynomials. And I don't know why. So what's also interesting is if you use this matrix, that polynomial is still invariant. So you can check that as well. So in fact, this polynomial is invariant under the reflection group generated by these two matrices. because since these matrices generate all of the transformations, this polynomial will be invariant under any matrix you make of any multiplication combination of these two. So,
I'm gonna write that down.
yeah, so the group generated by, let's just go 1, 1, 0, 1, and 1, -1, because we're on F3, and in F3, that's the only choice A could be, has x cubed minus xy squared as an invariant polynomial. Okay. Now, these polynomials for reflection groups over F3 are also well known, although not as like old. So, for instance, the 1900s was when the what's called the general linear group was just all invertible matrices over FQ. That's when that was discovered for what all of the invariant polynomials were. So, you know, we as mathematicians are perverse and we like to find more things to study. So one thing we might look at is, what about, I'm going to call this an ideal. This is an ideal. And what this means is, here m is an integer that's positive, so m is a natural number. Huh?
P still represents prime number.
He's the same kind, yeah.
And that's x to the power p to the m?
P to the m, yeah. So this ideal, what it's gonna do is it's gonna eat monomials that have x to the p to the m or y to the p to the m as a factor. So, and m equals 1, x cubed minus xy squared plus this ideal, this is how you would write it, is going to be the same thing as negative xy squared plus this ideal because it eats this first term. It's like the modular arithmetic but on steroids that we did earlier. So,
Because like that one, 8 3s,
yeah,
just sort of incorporate them in.
yeah.
Okay, and this one's eating x cubed and y cubed.
And anything that's a multiple of it as well.
So x to the 6 could go.
Mm-hmm.
So
X to the
if
sixth?
equal y, they-
No, like.
Wait, x is just 2 x cubed.
X
Go.
cubed or x to the.
X to the 6 also goes. Anything that's a factor, so it's even
Oh,
stronger.
factor.
It's even stronger than F, the other version.
So if x equal y also, if it is right?
Well, yeah, but
If x equal y.
right, yes. You could make that ideal, but then that just becomes your regular polynomial that
Yeah.
has X. Yeah.
So maybe you make a condition over there, you don't want x to be y. Because
Yeah. So here we're assuming X and Y are
it will be
different.
trivial.
Yeah. So X to the 4th Y plus the ideal is just, in this case, we think of it as 0. It's just the ideal. And so we kind of name that as 0 in some sense. Because x cubed is a factor of this.
But then you have lots of zeros.
Yes. Yeah. So why is this ideal particularly interesting to this reflection group? Well, as it turns out, because of Freshman's dream, the matrix action sends things in the ideal back to the ideal. So 0 always gets sent back to 0, and if it wasn't 0, it won't go to 0. So essentially, it behaves nicely with this action. So I won't have time to do everything that I wanted to do, so because it's almost time. So I'm gonna just sort of skip. So there's some other stuff that I wanted to do with counting that we won't get to. But what I did is I counted for my theorem. So this is me and my advisor. What I did is I counted the dimension of the vector spaces created by the invariant polynomials, because as it turns out, invariant polynomials form a vector space, which is also non-trivial. That group, I'll just call it, yeah, that group. On, we'll just say f of x, y, we'll say p, mod that ideal. And if you're curious,
That ideal?
yes, that specific
That
idea,
specific
except for
idea.
m could be any integer, any positive integer.
Oh, okay.
And I did it in more generality than that. I did it over any dimensional, any n dimension, and for any powerful prime also. And so what you get if you wanted to count it is if you know anything about how in calculus, which I was going to go into so that you didn't have to know this, but I didn't have time. So this is just a little fun tidbit for those who do know or remember how series can be represented, or polynomials, infinite polynomials can be represented as a short little, like how
Some of
1
the
over 1
geometry.
minus x equals 1 plus x plus x. So you get this. This is for any p and any m here, t is just a dummy variable. Happens what I did.
Wait, that's the dimension? That number's the dimension?
Of all the, it counts, it keeps track of the dimensions for each vector space it creates, because you would just consider anything of degree 1 to be its own vector space in some sense, anything of degree 2 of its own vector space, and it's counting all of them and keeping track of it by the degree in the dummy variable.
So that's the generator.
That's the generating function.
And
And
that
if
comes out to a whole number, or can it be a fractional? I mean, that doesn't,
No,
it's not obviously a
counting
whole.
dimensions, so it's not, that's what's interesting, that's why people study this. It's not obvious that this would be integer coefficients, and the fact that you can prove it's counting a vector space's dimension proves without like anything arduous in terms of like combinatorics that this is integer. And so what this is a small case of a general conjecture by Lewis, Reiner, and Stanton about a generalization of the binomial coefficient called the QT binomial coefficient. And so this is still unproven, that the QT binomial coefficient is counting for the bigger group, one that has all invertible matrices. And the goal in this was to do it for one hyperplane and then add in more hyperplanes to build up to the full group, which, let's be honest, I'm never going to do. Because I'm teaching here. And that's it.
All right,
Thank
thank
you.
you.
The paper online, you're welcome to look at it. This is a printed copy. Look at it if you want, but I don't even understand it anymore, so.
That's 58.
Yeah.
This is your paper that you don't understand anymore?
Yeah, that I have to do work to remember and understand
yeah.
again.
You don't use it.
Yeah,
You lose it.
it's all gone. Writing this talk was really hard, actually.
Yeah,
Thank
thank you.
Especially with us all asking questions, it really was tremendous. You did
Oh, thank you.
tremendous job. Yeah.
So I'm happy to in future give more talks, not like in immediate future, but like
Theoretically.
yeah, in like a couple months, like talk more about